And let me make this one last announcement while this is coming up. I don't know if y'all been watching or listening to the news, but there's a school close by to us, ITT Tech. I remember when they built the building and opened, and they have now closed, okay? And those students were given no warning. They showed up at the beginning of fall term. The doors were locked. They couldn't get in. The school was closed. Kaput. Well, some of them probably had already registered, all that kind of stuff, and they had nowhere to go. So what we're trying to do is handle as many of those as we can. Is here in Bessemer, but we're having this thing open house over in Birmingham today, and I've invited them to come by, and I'm required to be there. It's running 3 to something or another. I was late for the meeting yesterday because I had a calculus class here, and I had to finish it and drive over there. So I missed the time. I know it starts at 3, but I don't know how long it goes. So if you happen to know of any of those students or anyone else who didn't make the fall cut, we are offering extra courses in second mini term for those students. Y'all can participate in that. Anyone else you know can participate in those as well. We beefed up our second mini term offerings mostly for that. So normally today, my office hours would be from 12:15 till 4:45, but I will be leaving this campus no later than 2:30 to be over there by 3. So I won't be here until 4:45 today. I'll be over there until probably 5:15 or late. Well, I can't be much later unless I'm required to be. I'll have to get my wife to take care of something if I got to be at a business in Homewood before 6 o'clock. So if I can't be there, then I'll have to get her to cover that. But I'll be over there rather than over here the rest of the afternoon. Then tomorrow we're having something on this campus. I believe it's running 10 till 2 is what I heard. And of course, I've got class at 10, at 11. And I have a very small lunch break. I can participate in that. And then I've got class again at 12:15, and it goes until 2. So I won't be able to participate much tomorrow. So I've got to go over and do it today. All right. Any questions before we get going? Okay. Where we left off last time, we're just about to talk about increasing and decreasing functions. Now, looking at a function, not particularly easy to visualize when it's increasing and decreasing. However, draw the graph of that function, piece of cake, pretty much. Okay? The more you know about the graph of a function, sorry, the board is so nasty. You know about the function itself. Consider the graph shown here. We don't even know that function, but looking at a graph, we can tell a lot about it. In the range, what is the, okay, I shouldn't say range. What is the domain of that function? -2 to 4. What's the range? 1 to 4. And both of those, I heard brackets around them, right? Okay, because the endpoints are included on all those things. Now, when we talk about, yes? It's page 52. Okay, all right. When we talk about a function and talking about where it's increasing, where it's decreasing, we always refer to, okay, it's a little strange, but it's true. We're talking, decreasing means the y value is decreasing. But we refer to the interval in which it's decreasing according to x. So where is this function decreasing? From -2 to 0, it's decreasing. Decreasing in value from 4 to 1, but the functions is decreasing from -2. You always refer to the x, the independent variable, okay? Now, this has something other than increasing and decreasing. This has a period in there where it's constant, okay? Where would this be constant? 0 to 2. The constant value 1, but it's constant from 0 to 2 on x. And then where is it increasing? From 2 to 4. The values are going from 1 to 4, but the function is increasing from x equal 2 to x equal 4 inclusive. Now, when you're talking about increasing and decreasing, it really doesn't matter much what you do with the symbols here. This one technically to me should be a bracket here and a bracket there, a bracket here and a bracket there. However, it's not really all that important. Most of the time they just refer to them open-ended, okay? So don't sweat that too much, okay? But you're always moving, as they say here, left to right. You start at someplace on the left and always are moving to the right. So your intervals are always increasing in x. From -2 to 0, increasing. 0 to 2, increasing. 2 to 4, increasing. So the x's are always increasing. But what we're talking about is what the functional values are doing. Decreasing, constant, increasing. Okay? So don't let those competing phraseology, get in your way. Okay? You're talking about what the function is doing, but you're talking about it on regions of x. So a function is increasing, f is increasing on an interval when for any x1 and x2 in that interval, where x1 is less than x2, okay, you're picking any two values on that interval, okay, and x1 always to the left of x2. Remember, these on the horizontal, the independent variable axis. This implies if it's an increasing function that f of x1 has to be less than f of x2, because as you're going left to right, the function has to be increasing. Okay, does that make sense? Remember, the f's are your y's. They're increasing. A function is decreasing on an interval when for any x1 and x2 in that interval where x1 is less than x2. That implies that f of x1 is greater than f of x2 for every x1 and x2 within that interval. That means the function is going downhill as you're going left to right. Function is constant on an interval when for any x1 and x2 that's in that interval, f of x1 is always equal to f of x2. That means it's constant. The y's are the same. Make sense? This is math speak. The other is visual. Okay? So let's take a look at these functions. Okay? What would you say about the first one? Use the graphs to describe increasing, decreasing, or constant behavior of the functions. I don't need to cover anything because of all the answers are given. They're not. What would you say about A there? Increasing from where to where? All real numbers. Actually, from negative infinity to positive infinity. Why do we say that? There's no dot at the end. Okay? It means it goes on forever. And indeed, this is an increasing function. Now, someone may argue, hey, looky here. Right in there, right near 0, it looks like it's constant, doesn't it? Would you agree with that? Okay. It may look that way. Okay. I've got to find Sean. I know she's in here. There you are. Okay. All right. Anyone else come in since the called roll? Now, here's how you can do. Pick one of those numbers you think is close to being constant. This is 1. That would be a half. That would be a quarter. Maybe 1/8. Negative 1/8. Negative 1/8. This would be equal to negative 1/8 cubed, which is negative 1 cubed, which is negative 1 over 8 cubed, which is 64 times 8. It's a very, very, very small number, but it is slightly negative. Slightly negative. And the closer you get closer to 0, but it's always increasing. And then you get on the positive side. Now it's increasing just as slowly. So no, that's not ever constant. It's close to it, but not. Okay. So yeah, that's increasing from negative infinity to infinity. Okay? How about number B? Letter B. How would you talk about the increasing, decreasing, and constant behavior of that function? You tell me. Okay, starting increasing from negative infinity to negative 1. The x values to here, that's where it stops increasing, right there. And decreasing from negative 1 to 1, exactly, going downhill from there, and then increasing from 1 to infinity. And when you are expressing this, if you do them in interval notation, you can put parentheses around those intervals. Negative infinity, that always has a parentheses to negative 1, negative 1 to positive 1, positive 1 to infinity. Don't worry when you talk about intervals, put them in parentheses. Don't worry about less than is equal to brackets and stuff. Just put them in parentheses. All right, how about the next one? C. Increasing from negative infinity to 0. Very good. Stops increasing there, and then, second, constant from 0 to 2, and then decreasing from 2 to positive infinity. And again, if you're putting the interval notation, negative infinity to 0, 0 to 2, 2 to infinity. Notice, okay, this is what they call, remember, a piecewise defined function, linear function. To the left, it's constant function. They put the equal signs there. You could have put on either place. And then a negative slope linear function going there. So sure enough, that is exactly what we see. But when you talk about the intervals, parentheses are fine. You don't need to worry that those are equal there. Don't worry about it in this case. So let's see how they answer this. First function, increasing over the entire real number line, for all real numbers. They don't even list the interval. You could say negative infinity to positive infinity, all real numbers. Okay, that function, increase on the interval, negative infinity to negative 1. Notice how they put a parentheses there. Don't worry about brackets. Decreasing from negative 1 to positive 1, increasing again from 1 to infinity. Because technically, what is it doing right at that high point and low point? You don't know. It's not increasing or decreasing, so leave them out, okay? Don't then get the fussing with it. All right? This one, that's the one that's straight line up, flat, straight line down. The function is increasing the interval, negative infinity to 0, constant 0 to 2, and decreasing 2 to infinity. Notice they just put parentheses around there. When you talk about intervals, don't sweat the brackets, just put parentheses. Does that make sense? Any questions? Y'all are picking up on that really nicely. To help you decide whether a function is increasing, decreasing, or constant on an interval, you can evaluate the function at several values of x. Okay? It can take a while, okay? However, you'll need calculus, yay, to determine for certain the intervals on which the function is increasing, decreasing, or constant. Okay? So I hope to see you in a couple of terms. Yes, okay. All right. How many of you are in majors that you will be taking calculus? All right, good deal. Excellent. So you'll be in trig next term, right? Okay, so you need 113 before you do the calculus. Very good. All right. Because guess what? You can't evaluate every point and determine every one. Calculus can do it pretty easily. The points at which a function, this light is terrible glare on the board. The points at which a function changes. No, it's the light from outside that's glaring. But if I do that, try that, flip the lights on the switches behind you. I think it makes it harder for y'all to see if this is. See, now that's really easy to see. But you see, I still got the glare up and turned on the other one, is what he was saying, going closer to the door. No, that really bleeds it out. So I think that's harder for you to see. So I'm okay. I'm just afraid Tyler will fall asleep if we have it this call. We gotta watch that. His snoring. Oh yeah. Okay. Now, it's up to you. Do y'all want it dark or you're okay? That light wasn't bothering me. It's the light from outside coming glaring off the window is what I'm having trouble with. So this is easier for y'all to read probably. So let's now talk about the points at which the function changes its behavior, increasing to decreasing, or decreasing to constant, or constant to decrease, whatever. Okay. These points are helpful in determining the relative minimum or relative maximum values of a function. Okay? And again, in calculus, this is something that we pay a lot of attention to because in a lot of applications, that's really important. For instance, where is the point where your profit goes from negative to 0 to positive? That's going to be an important point, okay? Or when does it optimize, okay? Maybe you're doing well here, but anything past that, it starts going down again. That you want to know. You want to know that optimum point. Those are called your relative minimums or relative maximums. So here's the definition of those. A function value f of a, now this is your function, evaluated some value a, okay, is called a relative minimum of f when there exists an interval x1 to x2 that contains somewhere in that interval the number a, okay? x1 is less than a, x2 greater than a, okay? Such that x1 is less than x, and x is less than x2. This covers the whole interval in between those. And a is somewhere, one of those x's in the middle there. And this implies that for every x in that interval, your f of a is always less than any of the other values x between x1 and x2. That means the value, the function value, is a minimum. That's what we mean by a relative minimum. Function value f of a is called a relative maximum of f, and there exists on some interval, x1 to x2, a is somewhere in there, and other x's are in there as well. And as long as the x is in between x1 and x2, and that also, one of those x's is a, that implies f of a is greater than or equal to all those other f of x's there. Okay? That means you have a relative maximum. Blah, blah, blah on words, right? Okay? Let's see the pictures, and I think it makes a lot more sense. Okay? Here's what they're talking about. Let's call this our a value here. X equal a, right there. For all x's around a, x1 on the left of a, x2 on the right of a, for all the values x is in here, around that a, all the other f of x's here are greater than or equal to f of a, or in other words, f of a is less than or equal to all them, relative minimum. Pretty obvious, right? On a graph, it pops right out at you. Relative maximum, here's one. Let's call this one b. For all values x around b, x of 1 here, x of 2 on the other side of b, b is somewhere in the middle, all those other x's in here, f of b is always greater than or equal to f of x, all those other x's in that interval around b. Same thing here. Let's call this one c. For x's, x1 on this side, x2 on this side, around c, and other x's in there, for those other x's in there, f of c is always less than or equal to all those other f values here. Right? And another relative maximum, let's call that one d. Around that d, x1 here, x2 there, other x's in between, all those other x's in between, x1 and x2, f of d is greater than or equal to all the other f values, relative maximum. Okay? Looking at a graph. Okay, now why do we call them relative? They third cousins or something? Okay. Give you a little hint. This looks like it could be an absolute minimum. remember this one could be continuing down here, and then this isn't an absolute minimum. It's just relative to the values around it. That's your minimum. Okay? This is certainly not an absolute maximum. That beats it by a lot. This will beat it by. Yeah, okay? And this, if that keeps going up, that could beat it. So just relative to the points around it, that's a maximum. Same thing here. That's certainly not absolute minimum. Several over here are less than that. And that could easily be less than that if it continues downward. So this would be a relative minimum. All the values close around it, that's your minimum. Same thing here. That looks like it could be an absolute maximum unless this keeps on trucking upward. You know, and if it does, that would be absolute. It would just be relative to the points nearby. Okay? It's like you're the strongest kid on the block. 2 blocks over, guys can beat you up like crazy. But, you know, you're on the block, relative, you're the biggest. Okay, never mind. Violent. Okay, why did we go there? It's your fault. Okay. Okay. Increasing and decreasing functions. You will study a technique for finding the exact point of a second-degree polynomial function has a relative minimum or maximum. Second-degree polynomial, what's another name for that? Sounds like a 4, but it's not. We call a second-degree polynomial function. We haven't had it. Say again? Quadratic, yes, a quadratic function. Quadratic functions will have either one maximum or one minimum, and that's all, folks. Okay. Now, and those are absolute, by the way. For the time being, however, we'll use the graphing utility or pen and pencil to find reasonable approximations for those points. Okay? Once you get to calculus, you can find exact. Can't wait, can you? Okay. Let's see. Don't want to get ahead or behind where I need to be here. It looks like to me they skip example 5. Okay? So, yuck, I forgot to do this. Sorry about this, folks. For people watching at home, you'll notice it's harder to see because I forgot to get out of presenter view. I was using it, but I forgot about it. Okay, let me have to go through all this mess. All right. Good deal. Okay, let's do example 5. Okay. Let's try it on this page where we are now. It says use a graphing utility to approximate the relative minimum of this function. Oops, need to get my, let's see, get rid of that. All right, hold on just a second. We're having a slumber party in here now. So. This would be, is it James? Yes, sir. Okay, good deal. All right, we are all, hey, of the people who have shown up to class, perfect attendance today, folks. Way to go. Keep it up. Every day. There's still a couple people we've never seen. I don't think we'll see them. And I just noticed we did have someone withdraw. So, of those left, everyone here. Way to go. I'm sorry? One more time. Yeah. Okay, it doesn't. Okay. That's our question. From what I understand your question, your attendance, does that affect your grade? Is that what you're asking?
Does it affect anything else other than our grade in this class? Our attendance to come to this class?
Okay. All right. Number one, let me hit part of that question. If you're here, you get to ask questions, you hear, see what I'm doing, you participate and stuff. I think that improves your chances of doing well. So in that sense, it improves your grade. I don't grade on attendance.
No, I'm saying, do you take attendance for yourself?
Okay. No, we're required to. Okay.
So administration keeps track of our attendance.
Yeah. Okay. Yeah, okay. What I do, because it's convenient for me, I put it in a book, and then this afternoon, if I have a chance, I'll go in and put it on the system. You have, your student suite, we have an employee suite. And in that employee suite, there's a place to do attendance, and we're required to do that. If we don't, they start slapping our wrists. Now,
what is attendance fit as far as?
okay. It depends on who you are and other things. If you're on VA or WIA or some of those other programs like that, if you don't come to class, they may actually take away your benefit. So that's one reason we take attendance, because we don't know who's on what, okay? So we take attendance for everybody. Attendance at the first of the term is very important for people who are on Pell Grant, because if you haven't been to class, you're not getting, if you have a refund check, you're not getting it until you show up at class. So that's the main reason we take attendance. But these other programs require you to be there a certain percentage of time, okay? And there's another little subtle one there. If you notice on the college calendar, there will be a place where it says the 60% completion, okay? If it's the full-term course, that comes sometime in probably late October, early November. If you're on a mini-term, it'll be some other time. If you withdraw before that, okay, you finish the 60%, you may owe money back if you had, say, scholarship or other thing. If you're past the 60% mark, usually there's no penalty, okay? I say usually because different programs could have different things. So there's all sorts of little subtle things that I don't know but little beans about. I don't know how they administer it, but that all could be affected by attendance.
I was just wondering, nobody's ever explained it.
Yeah.
I don't understand why nobody's ever told us about it.
Okay, and that's probably a lousy explanation. It's the best I got right now.
I totally understood what you were saying.
Yeah, okay, good. Okay, something must be wrong. No, I'm sorry. Okay. Did I say something right? No. All right. So we were going to do example 5, approximating a relative minimum. F of x, oh, here's what I was trying to do. Okay. One of my other students in another class noted these little things down here. Notice a lot of times you can't see it, but since I held the pen near it, you can. And if I hit that, now I get my pen. And if I hit that, I change colors. I hope it didn't do anything. There it goes. Yeah, okay. So here's our f of x. Goodness, this is so bizarre. F. What is it doing? This is the strangest program. F of x, okay, forget that one over there, it's bizarre. Okay, f of x is equal to 3x squared minus 4x minus 2, okay? It says use a graphing utility. Now, if any of you have a graphing calculator, good time to use it, okay? If you know how to enter that, you certainly can, and then you can estimate that minimum point. There's a way to do it. If you need help with that, see me after class, okay? I know several of you do have graphing utility. For those of us without a graphing calculator, then what we have to do is some good old trial and error, okay? Now, what's a really simple x value to start with? Okay, time out again. Remember this thing up here? What kind of function is this? Second degree polynomial called a quadratic function, okay? That tells us it either is going to have a relative minimum or a relative max, one and only one. In fact, let me tell you this right now. Find the maximum exponent, which is also called the degree of that polynomial. Subtract 1 from it, and that's the maximum number of relative minimum or maximum you can have. And what's 2 minus 1? 1. You're guaranteed to have either a relative minimum or a relative maximum. Okay? So I'd say pick a point. And there's one that's really simple. X, what do you say? 0. Excellent. X equals 0. And what is your y? Can you look at it and tell? Negative 2, because that 0, that would be negative 2. F of x is y. So, when x is 0, y, or f of x, is equal to negative 2. So give me another x, one side or the other. 1, that sounds like a capital 1 to do. Let's choose 1, okay? Now, that takes a little more effort, but we can do it. We're a good, strong, sturdy people. F of 1 is equal to what? It's not that hard. Second, 3, negative 4, negative 2. Notice when x is 1, no matter what you do to it, it's still 1, right? Square it, cube it, whatever, it's still 1. Okay? So that gives you just your sum of your coefficients. And what does that come out being? Negative what? Negative 3. Okay. Now guess what we said before? We have one maximum or one minimum. Okay? So here at 0, we're negative 2. At 1, we're negative 3. I can do a little graph if you want me to, if it doesn't change page on me. So here's 0, negative 1, negative 2, negative 3, plus 1, plus 2, plus 3. And, ooh, I didn't leave enough, did I? At 0, we were at negative 1, negative 2. At 1, we're at negative 3. So, it looks like if it has a relative maximum, it's going to be somewhere here. If it has a relative minimum, it's going to be somewhere there, right? Because it's going downhill here, uphill this way, okay? So, let me give you another hint. For quadratics, this is jumping ahead, okay? This is jumping ahead. For a quadratic, look at the sign of your leading coefficient. What's the sign of that leading coefficient? Positive, okay? Now that tells you something. I don't know if you know what it tells you now, but here's what it tells you. If that's positive, that means it's cupping upward. That means you got a relative minimum. If that were a negative, that means it's cupping downward. That parabola is going downhill. That means you have a relative maximum. So which way should we look for our relative minimum? To the left or to the right? Because this is positive. Look to the right. So give me a value to the right. What's right of 1? 2. All right, f of 2. That would be, this time it's going to be a little more work. 3 times 4 minus 4 times 2 minus 2. This is going to be 12 minus 8 minus 2. Guess what that gives you? What? Positive 2. So when x is 2, this is positive 2. Whoa, look at what's happened here. You've got way up to here. So guess what? It's got a relative minimum. It's somewhere between 0 and 2. Question is, do you think it's closer between 0 and 1 or between 1 and 2? For a minimum. Here's another thing about parabolae. They're symmetric. Symmetric up or symmetric down. So therefore, this one's got to be between these two, 0 and 1. So now I say, give me a value between 0 and 1. Oh boy, our good old fractions, huh? F of 1/2. Now you can either do 1/2 or 0.5, I don't care which. Probably on a calculator you'd want to use 0.5. By hand I'm going to stick with 1/2 probably. This will be 3 times, what is 1/2 squared? 1/4 minus 4 times help me, 1/2 minus 2. Okay? Well, 3 times 1/4, I know what that is. That's 3/4. Okay? And then 1/2 of 2, 1/2 of 4 is, of negative 4 would be negative 2 minus 2. So what does that come out being? 3 1/4, right? So f of 1/2 is 3 1/4, or negative 3 1/4. Sorry about that. All right. Is that right? Yeah, -4 plus 1/3 would be -3 1/4. So, halfway between those, you're even less than -3. Okay? -3 1/4. Now, what you reckon you're closer to? Are you closer to 0 or closer to 1? Remember, it's got to be symmetric. This is closer to this, so it don't have to be in between there. So pick a number between 1/2 and 1. 3/4. You can go on like this. You see the pattern? Okay? If you're using a calculator, I would probably go with decimals, okay? And if you keep heading that way, you're zooming in on that relative minimum, okay? Something in between there. Already we're within, we're really close to it, okay? And I just am running out of room, so I'm not going to do 3/4, but you see how to proceed. And then whichever one it's closest to, go in between those two on the X. Get a new value. Then whichever it's closer to, zoom in. This isn't exactly what they had in mind, but a very famous mathematician named Archimedes, okay? He was quite a thinker, incredible thinker, quite an engineer, quite an inventor. I mean, he was an incredible, and he was way back BC, way back BC, like 400 BC or so, way back there. He was trying to figure out, is there any way to get the circumference of a circle? Okay, if you think about it, it's a really hard thing to measure. You have to have a flexible tape and keep it right on the thing, and it's really hard to do. Try it sometime. Really hard to do. So he came up with this method of, let's take, say, a square. He drew a circle. He put the largest square he could inside the circle and the largest square he could outside the circle. He can get the perimeter of the square, inside and outside, and you know the circle's going to be in between. Well then, that's a 4-sided figure. Then he did it with pentagons. And then he did it with hexagons. And then he did it with septagons and octagons and nonagons and decagons, and just kept going. And he was getting closer and closer to the values and taking the average. And he came really, really close to finding the circumference of the circle. Okay? You know what he called that method? The method of exhaustion. Okay? He kept going until he said, I'm tired, that's close enough for me. Okay, close enough for Gulliver. You can do sort of the same thing here. Keep getting closer and closer and closer until you say, okay, I'm tired, I'm exhausted, that's close enough. It's something between 1/2 and 3/4. Or, we don't know which side of that, so between 1/2 and 1, okay? And when you do 3/4, you'll know it's either between 1/2 and 3/4 or between 3/4 and 1. So you keep going until you say, okay, guess what? That's close enough for me. Now, that'll work generally. What did they get in the book? They stopped at 0.67, which is 2/3. And that's still an approximation. When you get to calculus, and a lot less time, you can zip exactly the value of that minimum. Can't wait to get there, can you? Good deal. All right. Now let's talk about average rate of change. Okay? I'm going to leave that. I was going to erase it. Who cares? All right. Average rate of change. Have we done this before? Yes, we have. We had a different name for it. Okay? Whenever you see rate, that sort of sounds like the same. It is the same root as the word ratio. What does ratio mean? Comparison of two numbers in what sense? Division, exactly. Have we done anything with division before? Yes, what do we call that thing? Difference quotient, very good. Average rate of change is almost just another way of saying a difference quotient. We have learned that the slope of a line gives you the rate at which it's changing, right? It's going up so many for how many went over. That's the division, rise over run. That's a division. That's a rate. Okay? The slope of a line can be interpreted as a rate of change. For a nonlinear graph whose slope changes at every single point, okay, like this one. This slope here is there, here it's there, here it's there. It's changing ever so slightly till here it's 0, then it's negative and negative. It's changing all along there, okay? So it's really hard, until you get to calculus, to give what the slope is at any point, but we can talk about the average rate of change between 2 points. So let's say one point is at x1, f of x1, and the other is at x2, f of x2. Okay? What's the average rate of change between those 2 points? Well, what would you guess you would do? This forms a line. What can you tell me about a line? It's downhill racer. Slope. Okay? The slope. How would you get the slope? Rise over run. How do you get the rise? Difference between the y's. That's how far up or down you're going. That's on the vertical axis, up or down. So it's f2, f of x2 minus f of x1 divided by rise over run. Run is x2 minus x1. That's how far you ran to get there. Okay? If you were climbing Oak Mountain, okay, you would go so many lateral feet, horizontal, so many vertical feet, rise over run. That would be the slope that you were going up Oak Mountain. Okay? And what was that? F of x2 minus f of x1 over the difference between x2 and x1, your difference quotient. Ratio, quotient, difference. It's the same thing, just called by a different name. Okay? All right. We use this concept a little more in physics. In pure math, you use the h, that's what you divide it by, which is the difference between the values. The other one we said, f of x plus h minus f of x divided by h. This is f of x2 minus f of x1 divided by x2 minus x1. It's the same thing. Line through 2 points is called the secant line. This is called a secant line. Okay? It connects 2 points on any old curve. Now, the slope of this line, you can sort of visualize what that is. That's your average rate of change. Say, when I drove in this morning, I'm going to just make you guess my average rate of change, or average speed, was maybe about 50 miles an hour. Does that mean I was driving 50 miles an hour on the expressway? No. I was going closer to 70 on the expressway. Maybe a little more once I got behind that slow truck, and it made me late. Okay? But back in town, before I got off on the expressway, if I was driving 50, I'd have had a little blue light flashing next to me, right? And after I got off the expressway. So I wasn't at any time, or very little, going exactly 50 miles an hour. That was my average rate of change. Sometimes I was going faster, sometimes slower. Well, here's your average rate of change on the secant line. There's really only, in this particular problem, only one time in that whole trip that my instantaneous rate of change was exactly the same as that. Down here I was going faster, here I was going slower. Positive, negative, okay? Right about here, it looks like that's about parallel. Now, if I were right there, parallel to that, what kind of line would you call that? A what?
Parallel lines.
Okay, parallel to that, but how would it be related to that curve? It's not a secant between 2 points on the curve. It would be only technically touching 1 point, but parallel to this. You want to know what you call that? A tangent line. Whoever said it. Very good. Tangent line. So a secant line, as you get those 2 points closer and closer together, gets closer and closer to the slope of this tangent line. But that's a different issue. That's getting into calculus. All right. So the line through any 2 points is called the secant line, and the slope of that line is noted as M, meaning slope of the secant line. SEC for secant, not southeast circumference. Okay. The average rate of change from F of F from x1 to x2 would then be f of x2 minus f of x1 over x2 minus x1. Before, and the quotient, different quotient is f of x plus h minus f of x over x plus h minus x, which is just h. So you see it's the same thing, basically. Change of y over change of x, slope of the secant line. Okay? Let's do example 6. Average rate of change of the function f of x equal x cubed minus 3x from x1 being negative 2 to x2 being negative 1. What's the average rate of change there? How would we do that? Average rate of change. What would that be? What's the formula? Y'all slept through the last slide, right? Turn on those lights. Okay, never mind. Okay. F of what? Of x what? 2 minus f of x1 divided by x2 minus x1. Rise over run. Got it. Plug and chug. What is f of x2? x2 is negative 1. So that'd be f of negative 1 minus, what was x1? Negative 2 divided by, what was x2? Negative 1 minus, what was x1? A negative 2. Be careful with the signs there. Put parentheses when you need to. All right, we got to figure out what f of negative 1 is. So let's do that up here. F of minus 1 is equal to, what would that be? Plug and chug. Say again? Negative 1 cubed minus 3 times, help me, negative 1. What's negative 1 cubed? That's negative 1. It's negative 1 times negative 1 is 1 times negative 1 is negative 1. Okay? Negative 1. And what's negative 3 times negative 1? Plus 3, so that's going to be 2. So this will be 2 minus, let's do f of negative 2. And what would that be? Here's your f of x. That would be what? Not that hard. Negative 2 cubed minus 3 times negative 2. What's negative 2 cubed? Negative what? Negative 8. And what's negative 3 times negative 2? A little louder. Plus 6. So what does those add to? Negative 2. All right? So you had a 2 from your f of negative 1 minus a minus 2 from f of negative 2 divided by, can we go and do that denominator, or you want to write it down again? Let's do it. Negative 1 minus a minus 2 would be negative 1 plus 2, and the numerator would be 2 plus 2. Didn't know you'd be doing such high math today. 2 plus 2 over 1. That would be 4. There's your average rate of change between minus 2, 2, minus 2, minus 2. That's what the first value was. And minus 1 plus 2, that was your second value. Okay? So that's the line, that secant line has a slope of 4. Pretty steep. Okay? Now, let's do the B part. What is your average rate of change from x1 equals 0 to x2 equal positive 1? Okay? What's your formula? your equation for average rate of change? Whoa, why did that do that? Oh, there. Oh, this is being, oh, I know I'm too near the edge. If I'm over here, do y'all see that? It turns into something else, and when it's over here, it turns into a dot. Why? I don't know. I have to stay over here. So what's the formula? Alpha of x2 minus alpha of x1 divided by x2 minus x1. This time we got to figure out what's your x2? 1. So what's your alpha of 1? Remember, that wasn't too hard to do. Alpha of 1 would be what? A little louder. 1 minus 3, which would be negative 2. Remember, when you're plugging a 1 in for your x, that just becomes a 1, that becomes a 1. Everything's a 1. So you use your coefficient. 1 minus 3. That's negative 2. So your alpha negative of x2, which was 1, this is negative 2. Minus, I've been waiting for this one all day. What's alpha of 0? Is what? 0. Because it's 0 minus 0 is 0. Divided by, and 1 minus 0. So what would this slope be? Negative 2 over 1, which is negative 2. So from 0, 0 to 1, negative 2, your slope is negative 2. Positive 4 here, negative 2 there. So yeah, your average rate of change is changing pretty quick, okay? Does that make sense? Plug and chug is all that's involved here. Okay? Let's see how they did it. Average rate of change from x1, negative 2 to x2, negative 1 is alpha of x2 minus alpha of x1 divided by x2 minus x1. Now a little bit of a timeout here, okay? What if you switched your x1 and x2, okay? You actually had the x1 to the right of x2. Is that going to give you a wrong answer? As long as if you switch it here and switch it there, you're still going to get the same answer. So it doesn't matter which one you say is 1 and which one is 2, as long as once you do this one first here, you do that one first down here too. Okay? Doesn't really matter. Most of the time we'll let the larger, the one to the right, be the x2 and the other x1, but it really doesn't matter. Okay, proceed. Alpha of x2, which is negative 1, minus alpha of x1, which is negative 2. Okay? Divided by x2, which is negative 1, minus x1, which is negative 2. So it's minus 1 minus the negative 2. I get sloppy. I think everybody gets sloppy. We really should call this negative 1 minus negative 2. But yeah, if I see that little dash up, most of the time I'm going to call it minus. But really, this is negative, that's your minus, okay? Because this one's doing a subtraction, these two are just negating what follows it. But it really doesn't matter, okay? And we already calculated what alpha of negative 1 was. We went through that and found it to be what? 2. And alpha of negative 2 was negative 2, I think it was. And so that gave us 4 over 1, okay? So that's a 2 minus a minus 2 over, they skipped all the steps in there, but it's a negative 1 plus 2, which is a 1, and that gave you 4. Secant line has a positive slope, really steep positive slope of 4. In the second part, you do the same formula. The average rate of change is still the same thing. It's just you change your x1s and x2s. The x1 here was 0. The x2 is 1. Plug and chug and see what you get. 1 minus 0, that's easy to do in the denominator. That's going to be a 1. And that gave you a negative 2 minus 0 over 1 minus 0, which is negative 0 over 1, which is negative 2. Secant line had a pretty steep negative slope. Were there questions? I thought I saw a hand go up. Maybe not. Make sense? Average rate of change, awfully close to the same thing as difference quotient. Nothing too new here. It's the slope of a line. Okay. That was example 6. They skipped example 7. Do you want to do example 7? Yay or nay? What you think? I think we need the lights on, folks. No, okay. What do you think? Do it, okay? How are we doing on time? Okay? 5 minutes. We should be able to do this. The distance S in feet in a moving car from a stoplight is given as, this is a new problem here. Okay. New problem here. Never mind. Okay. S of t, distance from a stoplight in feet, is 20 times t to the 1/2 power. What in the world does that mean? T to the 1/2 power. There's another way of saying that. What is something? Ah! Okay, I saw them writing in the air. Square root. Okay? When you see a fractional exponent, this is your index in the radical, and this is your exponent within the radical. So that should be t to the 1/2 power over square root of 2. Okay. Now, does this make sense? Distance from a stoplight in terms of time. If you're at a stoplight, you're at time t equals 0. What's your distance from that stoplight? 0. Okay, better be. If it's a stoplight, you better be stopped right there. Then once you left it and it changed green, then the t increases and you're increasing slope. Okay? So, that's your distance from a stoplight in feet, I think it is. And t is in seconds. Find the average speed of the car from t1 equals 0 to t2 equals 4. So we're going from t1 equals 0 to t2 equals 4. And these are in seconds. Okay? So what's your average rate of change? It's what? F of t2 minus f of t1, t2 minus t1. Okay, I can do that denominator. Okay, what is your f of t2 then? Or it's not f, it's s. Okay, sorry about that. Let me get my eraser and change this f's to s's, because that's what we're dealing with. Okay, change back to a pen. S of t1 to minus f of t, s of t1. Okay. So what is s of t2? S of t2 is 4, 4. That would be 20 times, let's go on and write it the other way. In there, okay. The square root of 4. What's the square root of 4? 2, okay. And 2 times 20 is 40. So that would be 40. So that would be 40 minus, oh boy, this one's hard. What is S of 0? 0! Very good, okay. And what's your time difference there? T2 minus T1. 4 minus 0. What would that be? 10. 10 what? Feet per second, because your S was in feet and your time in second. 10 feet per second. Okay? I must have messed that up. Oh, I couldn't read. The lights are too dim. Sorry about this. This is supposed to be a 3/2. What in the world does that mean? That means you still take the square root. This is the index, but now what's in here, you cube it. So I got that wrong. Okay? Y'all are supposed to be watching out for me. You know, getting my back. And y'all just let me walk right into that one, didn't you? Okay. Whoops. For some reason, this isn't erasing. There we go. All right. Okay. Now, there's two ways you can do this. I know we're running out of time. This is a hint for future reference. When you have t to the 3/2, that means either one of two things. It either means the square root of t cubed, or it's the square root of t cubed. Either way you want to do it. You can bring the cube inside, or you can do the square root first and do it on the outside. This one, I suggest you do it this way. The square root of 2 we saw was, square root of 4, was 2, and then cube 2, and you've got 8, and 8 times 20 would be 160. That's what we should have had there. Okay? That should have been a 160. Ah. 160. So that would have been 40 feet per second. Okay. Sorry about that. We will pick up there for next time. Almost finished. Didn't quite. We'll pick up there for next time. Homework exercises, do either 7 or 9, either 11 or 13, any of the odds 15 to 23, any of the odds 25 to 29, any of the odds 31 to 37. Okay, I think we had assigned most of those before. No, those last ones we hadn't. So then add to that 39 to 45, 47 to 53, 55 to 59, and 61 or 63. And we'll pick up the rest of those next time. 61 or 63. Average rate of change. And where we'll begin next time, I'm going to turn this off because it's so bright in my eyes. Okay. And all right, good deal. We'll see you Thursday.